Thanks for having me here today. So I'm Manu, I'm a PhD student in my final year, and today I will be talking about what I've been doing during my PhD. So as you can guess from the title of the presentation, I focused on the first episodes of star formation, also known as population tree stars, and in particular I'm trying to understand if these stars left some kind of signature in the evolution of our universe. So this is the outline of the talk I'm going to give today. I'm going to start with a brief introduction. I assume that Monash is well known for being the stellar department, so probably not going to be much needed. And then I'm going to talk about the simulation that I've been using and developed, which is called meraxis. And then I'm going to talk about 3 interesting results that I found along with my PhD. So let's start with the introduction. So I always like to start my talk with the periodic table of elements, just to remind that astronomers, or at least some of us, we really like to simplify things, because out of all this table of elements, what I care about is hydrogen, helium, and all the rest, which we call metals. And the reason why we do that is because usually all these elements are produced inside stars or some kind of stellar process. So if we observe any star today, all these stars have like a variety of a chemical composition. They're not made just of hydrogen and helium. They have hydrogen, helium, and all these metals. So we are facing a little bit what we could call the chicken and the egg problem, because from one side we have our stars with all their elements, carbon, oxygen, nitrogen, and so on. But all these elements, we know that they have been produced inside stars. So which one came first, the stars or the elements? Now, since we know that Big Bang nucleosynthesis only produced hydrogen, helium, and a few traces of lithium, this means that these very first stars had to be formed only with these 2 elements. So the way in which we solve the problem is saying that at the beginning of star formation, the very first stars only had hydrogen and helium, and we call these stars population tree stars. Now, this is fancy, this is cool, but the problem is that as of today, we never observed these stars. Now we are getting closer and closer, I would say, that like in the past couple of years, there have been like a few candidates that have been detected, but not definitive detection yet. And this is a problem because this means that we basically have no constraint on the properties of these stars, and the only way in which we can try to constrain the properties of population tree stars is just by looking at a numerical hydrodynamical simulation. There are some hydrodynamical simulations that follow the collapse of a pristine gas cloud, and what numerical simulations seem to agree is that overall, these pop-3 stars might be more massive than the present-day stars, and this means that they can be much brighter, even if for a shorter amount of time. And also another thing that is important is that if we have like a cloud of pristine gas, it's more difficult to form stars. So they have a different star formation efficiency, or in other ways, it's like the gas is converted into star with a less efficient way. So this is really all you need to know to follow this talk about population tree stars. So since, as I said, we don't have any constraints on these pop-3 stars, throughout my PhD, I use this simulation, which is called meraxis. And the idea is that I'm trying to investigate what impact these stars have on the evolution of our universe, assuming different properties. So let's say all the pop-3 stars are all very, very massive. How would they influence the epoch of reionization or the metal pollution, the chemical pollution of the intergalactic medium? So to use this, to do this, I use meraxis. Meraxis is a semi-analytical model of galaxy formation, which is a simulation that is done in two parts. The first part is an n-body simulation, and then we post-process the output of this n-body simulation in order to add all the physics that is relevant for galaxy formation. So the first building block is the n-body simulation. This is just a pure dark matter only simulation. This is a cosmological simulation. This is a collisionless n-body simulation. And we run this simulation, and this simulation will provide us with all the information on the properties of the dark matter halos and also their spatial location. The n-body simulation that I use for this work is a high-resolution n-body simulation, at least for cosmological simulation, because we are able to resolve down to halos of 10 to the 5 solar masses, which is important because we think that the very first episode of star formation occurred in the smallest dark matter halos, which we call minihalos. Of course, like having this great resolution comes with a price. In particular, we need to we only have a relatively small volume, because this is like about 15 co-moving megaparsec, which again for a cosmological simulation is quite small. And we run this simulation from redshift 30 to 5. Redshift 30 again, where we think that the first stars form, and down to redshift 5 is because the reionization ended roughly at this redshift. So on top of that, so after we run our n-body, we run the semi-analytical model, which accounts for the physics of galaxy formation. Now, if you want to build a galaxy in a numerical simulation, there aren't that many processes that you have to take into account. So let's start with the dark matter halo, which is provided by the n-body simulation. So the first process that we need to account is the gas infall. So the gas particles will start to fall onto the potential well of the dark matter halo. And once we collect enough gas, some of this gas will cool down and settle in a sort of disk structure. So once we have enough cold gas, we can trigger the star formation. So we have stars forming that eventually they will explode as supernova. And so we have to account also for the supernova feedback, which is crucial because it ejects gas outside the disk, again into the halo, but it also pollutes the gas with metal, which is quite important to consider since we are focusing on population 3 stars. About this, we are also able to follow the metallicity not only within the galaxy, but also in the surrounding IGM. Because if the supernova explosions are powerful enough, the metals will be able to travel outside the virial boundary of the dark matter halo. And together with galaxy formation, we also compute reionization, and this is quite a unique feature for a semi-analytical model. So while stars are forming, we are also accounting for the production of the ionizing photons, which are responsible for the cosmic reionization. So during the first year of my PhD, I worked a lot on this simulation. I developed all the part that was related for population 3 star formation and minihalos. In particular, here I want to highlight that if we want to include POP3 stars, first of all, we need to account very accurately for the metallicity evolution of the galaxies and of the IGM, because the moment in which a galaxy becomes enriched with metals, that galaxy cannot form POP3 stars anymore. But also, since population 3 stars don't, as I said before, we have very few constraints, if some. Basically, we want to explore different scenarios. So Meraxis is built in a very flexible ways, for which all the main population 3 properties, like the initial mass function or the star formation efficiency, these are free parameters in the model that we can change during each run. And in particular, in this project, I focused on, I analyzed the 3 different initial mass functions these are all constrained between 1 and 500 solar masses. And the red is a salpeter, simple salpeter IMF, while the yellow and the blue are a log normal IMF. The yellow one is centered at 10 solar masses, while the blue is centered at 60 solar masses. So the choice of this initial mass function is sort of like to explore a variety of possible IMFs that have been suggested from detailed hydrodynamical simulations. And finally, I want to advertise briefly Meraxis, because after all this development on the physics of population 3 stars, we also made this code publicly available in case anyone is interested in collaborating or in developing any other features. So enough with the initial big introduction, and let's move on to some interesting results. So the first thing that I analyzed was how galaxies got their metals. So this brings back to this picture here, where we have all the pollution from the supernova feedback. So in order to compute this sort of bubble around the galaxy, which is filled with metal, we developed this bubble model, which is a simple analytical model developed around 20 years ago by Fulanetto and Loeb. So this can be summarized very briefly, saying that, well, supernova explosions release metals, and in particular, these metals are initially swept out with a velocity of roughly 300 kilometers per second until they mix in a very thin shell. And once we have the formation of this shell, basically the propagation of metals occurs in a bubble, within this bubble, and this bubble is expanding in time. So what we want to keep track is the growth of this bubble of metals, and this can be done through the set of Taylor model, which is summarized in this very simple equation. So this is in this equation we have the radius of the bubble, which depends on the numerator. We have the supernova explosion energy, the stellar mass, and the number of supernova per solar mass. Basically, in the numerator, we have more supernova we have, the more energetic the supernova is, the larger will be the radius of the bubble. And this expansion is growing, let's say, against the surrounding gas. So at the denominator, we have the number density of gas in which the explosion occurs. So once the bubble is propagating in the galaxy where the density is higher, of course, the propagation will be a bit slower, while once it gets out of the galaxy, it can increase its speed. And according to literature, using this simple model, we find that metal bubbles are quite small, because they at redshift 6 they will have a size of roughly 200 comoving kiloparsec. And this is consistent with what we found in our simulation. So basically, for each galaxy that is forming stars, we computed the value of this radius. We computed also the evolution of this radius. And you can see here, this is the distribution function of the radius of the bubble in comoving kiloparsec at 4 different redshifts. The left panel is a redshift 20, 15, 10, and then 5. And the gray vertical line highlights the value from 2009 of roughly 200 comoving kiloparsec. So as you can see, we are consistent, we're roughly consistent with this value, and only very few bubbles at redshift 5 exceed those values. So overall, these bubbles are quite small. So this already suggests us that probably most of the metal pollution will occur within the same galaxy. So the question is, how galaxies get their metals? Well, one channel would be what is called the internal enrichment. So basically, a galaxy will form stars, and from its own star formation, it will also self-enrich. Another interesting scenario is that if we have a galaxy like the one that is indicated with the arrow, well, rather than a galaxy, this is really like a dark matter halo with some gas that hasn't formed stars yet. But if this, let's say, proto-galaxy is next to a galaxy that already formed stars, and these two galaxies are close enough to each other, if that galaxy is inside the bubble of the metal bubbles from the originated from the galaxy that already formed stars, then that smaller galaxies can get metals from the star formation episode occurred in the other galaxy, in the star-forming galaxy. And we refer to this as external enrichment. So we investigated the relative occurrence of these two phenomena. So with the gray line, we have the internal enrichment, and with the black line, we have the external enrichment. So these are halo mass distribution function. And as you can see, at all the redshift from 20 to 5, the gray line is always significantly higher than the black line. So basically, galaxies of all masses are way more likely to have internal enrichment rather than external enrichment. However, there is an interesting tail here at redshift 5, a tail of low mass. So we're talking about 10 to the 6 to 10 to the 7 solar mass. So these are small galaxies that, since at redshift 5 we are well within the epoch of reionization, there is also the reionization feedback that is preventing these galaxies to form stars, these halos to form stars. So during reionization, low mass halos are actually more likely to be externally enriched rather than internally enriched. So these can have interesting implications for systems like the damped Lyman alpha systems that are really systems where we only have gas and not stars. And with the metallicity model that we implemented, we are also able to investigate global properties such as the average metallicity. This is like a 2D projection of our simulation, again at 4 different redshifts from 20 to 8. All the blue pixel highlight values with that are smaller than 10 to the minus 4 solar mass, while red pixels are above 10 to the minus 4 solar metallicity. The reason why I highlighted this 10 to the minus 4 solar metallicity is because this metallicity is often referred as a critical metallicity. So if a gas cloud has a metallicity lower than this value, so lower than 10 to the minus 4 solar, is more likely to form, it will actually form population tree stars. So this is the reason why I put this threshold at 10 to the minus 4. So from this picture, you can sort of see the progressive enrichment of the intergalactic medium. At redshift 20, all the simulation is blue, while at redshift 8, we start to see a lot of red pixels. And we can also compare this with the metal filling factor, which is simply like the ratio between the volume of the metal bubbles over the volume of the pixel or the simulation. So basically, this tells us what fraction in volume is enriched with metals. And all these two quantities correlate with the dark matter density field, because now in the bottom row I'm showing the dark matter density field, and this is expected because higher dense regions are also the one where we have more galaxies, so more star formation. And as a global picture, I'm also showing here the average metallicity as a function of redshift. So in the left panel, we have the average metallicity in solar metallicity. And again, I'm highlighting the 10 to the minus 4 value. So you can see that the average metallicity keeps increasing, and around redshift 12, it gets above the critical metallicity. So this is like roughly a redshift where we expect to not see a significant contribution of population tree stars anymore. And on the right panel, instead, I'm showing also the average filling factor, which again is the ratio of the volume that is enriched above the critical metallicity. And you can see that this is quite small. It's roughly is less than 1% at redshift 5. And this is interesting because it basically tells us that only a small portion of the universe is actually enriched above the critical metallicity. And this is a result that has been found also in other works using hydrodynamical simulation. And this is like a consequence of the fact that the bubbles, the metal bubbles, are quite small. Okay, so I'm going to move on to a second result that we found using population tree star formation model in meraxes. In particular, for this project, we focused on the JWST bright galaxies. As many of you, I'm sure, heard, like during the first 2 years of JWST, we found a great deal of very bright galaxies at redshift larger than 10. So at the time of this study, we did this like toward the end of 2023. So this was like a collection of the galaxies that were found above redshift 10, the bright galaxies above redshift 10. Now this picture is somehow outdated because 2 of the redshift 16 candidates disappear, but we also have 2 redshift 14 candidates that are spectroscopically confirmed. So there are a lot of bright galaxies at very high redshift. And to appreciate why this is a problem, here I'm showing different UV luminosity functions. So on the y-axis, we have a number density per unit of magnitude, and on the x-axis, we have UV magnitude. And the data points come from Hubble and JWST observation, while the black line is the UV luminosity function computed in meraxes. So you can see that in the lower panels, so redshift 8, 9, and 10, the line fits nicely all the data points. However, at higher redshift, so at redshift 13 and 16, we can see that these points are actually higher than the prediction. So since we are on the right part of the plot, we have a smaller magnitude meaning a larger luminosity. So basically, there is an excess of bright galaxies at redshift larger than 12. And this is not just a problem of meraxes. This is something that a lot of simulation are struggling to explain. So people come with all sorts of explanation for that. So maybe we have an increased, maybe the star formation efficiency is actually higher than what we expected, or the feedback was less strong than what we expect. Some other people even refer to this as a possible indication that there is some tension with the lambda CDM model. So the scenario that we explored here instead is that maybe some of these galaxies include POP3 stars. And the reason why we did that, we decided to investigate this scenario, is because, as I said at the beginning, POP3 stars can be brighter. And we want a mechanism that sort of boosts the UV luminosity function high redshift, but without losing the agreement at lower redshift. Because if we just say maybe the star formation efficiency is higher, this will boost the luminosity function not only at high redshift, but also at low redshift, where we have a lot of observation and we are well constrained to those observations. Instead, population tree stars, we expect them to form only at very high redshift and not a lower redshift. And so this would naturally explain why this boost would occur just at high redshift. So to do this, we implemented a model to compute the luminosity of a POP3 galaxy. So I'm going to start showing this plot, which on the y-axis, we have the absolute magnitude as a function of time. So let's assume that we are at redshift 8, and we have a star formation episode of 10 to the 5 solar mass. Now, and since we are doing this in a simulation, each snapshot, the time step between two consecutive snapshots is not 0, like each time step has a certain duration. In particular, at redshift 8, the time step of our simulation is about 13 million years. So that's why on the x-axis I'm showing 13 million years. So if we assume that we form, let's say, 10 to the 5 10 to the 5 solar mass in POP2 stars continuously throughout this snapshot, we will get a magnitude of -14, as shown in the red dashed line. If instead we are forming, again, continuously throughout the snapshot, 10 to the 5 solar mass of POP3 stars, then the luminosity will depend, of course, on the 3 different IMFs that I'm showing here, salpeter, log normal center at 10 and log normal center at 60 solar mass. So you can see that the black dashed line, of course, it will become higher and higher, having a more top-heavy IMF. And in particular, we can have POP3 stars that can be up to 1 magnitude brighter than POP2 galaxies. Now, assuming that POP3 stars form continuously throughout the snapshot is not really accurate for 2 reasons. One is because at high redshift we have more and more evidence that the star formation occurs in a single burst. But also because POP3 stars are also short-lived if they are more massive. And so this means that during the duration of this snapshot, once the first star form, they will also explode, and so they will influence the subsequent star formation within the same snapshot. So for this reason, we accounted for the fact that POP3 stars can form in a single burst at the beginning of the snapshot. And so now you will see that the luminosity of this system, the brightness of this system, will change with time. Because more time passes, more stars will have died out. And so you can see that for more extreme IMFs, like in the panel of in the right, the log E IMF, we can have very high peak, but also the luminosity will decrease quite quickly. And in such a case, we can have the POP3 galaxies can be up to 3 magnitude brighter than POP2 galaxies, assuming the same amount of stars is formed. So we implemented this model. Of course, the other thing that we need to take care of is that we can observe this, the episode of star formation in a random time. It's not that we will observe all these galaxies right after they form stars. We might observe them after several million years, and this will mean that the luminosity will actually be much fainter. And so we computed the UV luminosity function. In particular, here I'm showing just 2 very interesting redshifts, redshift 16 and redshift 12. The black line is the total UV luminosity function, and the cyan line is the luminosity function computed only from population 3 stars, population 3 galaxies. And the black data points are points from another simulation, while green and gray data points are the one from the early JWST observation. Again, this study was done in early 2024, so only very few data were available. So, and also to do this computation, I assume that the POP3 stars form in a single burst with the more extreme IMF, so the log normal centered at 60 solar mass. So if we focus on the panel on our left, redshift 16, you can see that the cyan and the black line superimpose to each other at the brighter magnitude. So this means that at redshift 16, all the brightest galaxies in this simulation host POP3 stars. Instead, if we move at redshift 12, the black line is higher than the cyan line. And so this means that only some of the brightest galaxies might contain population 3 stars. And if we move, like I'm not showing here the result at redshift smaller than 12, but basically the contribution of POP3 stars becomes totally negligible. And the black line is consistent with the HST and JWST result. So this provides a strong indication that a high redshift, in particular when I say high redshift, I say larger than 12, and around 16, the brightest galaxies might host population 3 stars. However, this is not the end of the story, because as you can see, the brightest galaxy in this simulation have a magnitude of -18, while some of the galaxies that have been found with JWST have a magnitude of -20. Now, the reason why we don't see these galaxies is because we did this study on a small box. As I said, it was a 15 co-moving megaparsec box, and this means that we don't sample a volume large enough in order to have the very high overdense region where we can actually have the more massive galaxies forming at the earliest epochs. So, while this result is a strong, gives an indication that a redshift larger than 12, a lot of bright galaxies might contain population 3 star. This is not like a definitive result in saying that all the brightest galaxies that we have seen with JWST have population 3 stars inside. And I want to conclude with a project that I'm working now at the moment. So this is still a lot of work in progress, which is focused on the 21 centimeter signal. So for the people in the room that are not familiar with this signal, so we have from the hydrogen hyperfine structure, which is given by the coupling between the nuclear and the electron spin. We have two different sublevels, and when we have a transition between these two different sublevels, we will have an emission of a photon at a wavelength of 21 centimeter. So since this is a spectral line, it will be affected by cosmological redshift. So if it is a redshift 10, it will be redshifted by a factor of 11. And this is, as I said, a low frequency radio transition that is emitted by neutral hydrogen. So this is very powerful if we want to study the intergalactic medium before the epoch of reionization. Because today, the intergalactic medium is all ionized hydrogen, so we have no emission of this signal. The 21 centimeter line that we are observing today only comes from galaxies. But a high redshift, before the epoch of reionization, the IGM is made mostly by neutral hydrogen. So we expect to see a lot of this signal coming from the entire sky. And we can quantify the strength of this signal using the differential brightness temperature. Now, I'm going to break down this equation. But the key message here is that we can get a lot of information on the properties of the IGM before the epoch of reionization using this signal. So, as I said, this is basically the quantity that defines the strength of the signal, the differential brightness temperature, and it depends on 4 key quantities. The first one is neutral hydrogen. Of course, if we don't have any neutral hydrogen, we will not have any emission of the signal, and the more neutral hydrogen we have, the stronger will be the signal. The second quantity is the density contrast. So this is the it's given by the density field. Again, a higher dense region means that they will have more hydrogen and so more signal. The third component is cosmology, in particular the content of baryon and matter in the energy density of the universe. And finally, the last term, which is the spin temperature of the gas. So the spin temperature of the gas is the temperature that defines the distribution of the energy level population between the two hyperfine levels. And as a first approximation, you can think of that as the kinetic temperature of the gas. So now we have a rough idea of what are the cosmological parameters, and we more or less can compute the density contrast from numerical simulation. Here, what we want to focus are the first and the last component, the amount of neutral hydrogen and the spin temperature. So the strength of this signal basically tells us how much hydrogen there is in the IGM and at what temperature it is. And this is determined by the radiative backgrounds that are effectively ionizing or heating up the IGM. In particular, we have ionizing photon, X-ray photons, Lyman alpha photons. And all these photons are mostly emitted by stars. So we have POP3 stars, POP2/1 stars, let's call them normal stars, and even accreting black holes, early accreting black holes. So actually, in my very first project I've done during my master and my PhD, my first year of my PhD, I used a different simulation in which we were able to compute the contribution to this signal from all this class of sources. So if you focus on the thin black line, this is the differential brightness temperature as a function of redshift plus 1. And you can see that we have the presence of an absorption throw, which is due to the change in the spin temperature evolution. And then this differential brightness temperature will start to increase, showing the heating of the IgM from the X-rays. If we account also population 3 stars, we will get the red dashed line. So as you can see, we will have that the radiative backgrounds will start to contribute much earlier than so a redshift around 20, 22, a redshift much higher compared than just the POP2 case. So this basically shows that at higher redshift, that POP3 stars have a contribution on the 21 centimeter signal at higher redshift. And the black the black thick line also includes for an extra heating contribution from accreting black holes and other exotic sources. So the whole point of this plot is that the shape of this curve changes if you're going to change the number of sources that you are accounting for. The problem is that this global signal, this is like a sky averaged quantity, and despite we have a lot of radio observatories that we are trying to detect this signal is likely not going to be observed in the near future because the sensitivity, the current sensitivity is much lower than what we need in order to observe like a brightness temperature of roughly minus 100 millikelvin. But this is not the end of the story, because while the 21 centimeter signal, global signal is very difficult to observe, what we can hope to observe is the 21 centimeter power spectrum. So basically the spatial variation of this signal. And in this work I use a simulation that it was not using like an n-body simulation, so we didn't have any information on the spatial location of these sources. But we can do this using Meraxes, because again, in Meraxes now we have POP3, POP2 stars. We have an n-body simulation, so we know where the emission comes from, so we have all the spatial information. So we just need to compute together with the ionizing photons also all the radiative backgrounds that are important for the 21 centimeter signal. So for example, the X-rays and the Lyman alpha photons. So here for this study we used a different n-body simulation, because now it's really important to use a box that is large enough in order to account for a volume that is representative of the entire universe. And of course this comes in expense of the resolution. So with this n-body we can resolve all dark matter halos down to 10 to the 7.5 solar masses. So this means that we cannot directly resolve minihalos. And so what we needed to do, it was to develop a subgrid model in order to estimate the missing background from minihalos. So we used a small box to estimate how much background is produced inside minihalos, and we sort of implemented inside the big box. And again, the whole point is having like a box that is large enough. So in this case we have a 300 co-moving megaparsec box, which is big enough to investigate reionization. So here I'm going to show this result that are still work in progress. We hope to get to finish this project within the end of this year. But so here I'm showing the 21 centimeter power spectrum, so the spatial variation as a function of redshift, for 3 different models. So the black line is a model that doesn't account for POP3 stars. The red line accounts for POP3 stars with a low sort of like emitting low X-ray background, and the cyan line is POP3 stars emitting a strong X-ray background. This is basically there is a lot of uncertainty on what is the actual X-ray contribution coming from the high mass X-ray binaries. And so for this reason, we added this extra parameter, which is basically the X-ray luminosity as a function of the star formation rate. Sorry, the ratio between the X-ray luminosity and the star formation rate. So the red line assumes that this ratio is something around 10 to the 40 erg per solar mass, while the cyan line is 2 orders of magnitudes higher. So as you can see, all these three lines are very different to each other. And in particular, it's really interesting to look around between redshift 10 and 7, because at this, in this redshift regime is where SKA is aiming to look at. So the power spectrum is really sensitive to POP3 star formation episodes, and these differences between redshift 7 and 10 are quite important. And the two panels here, I'm showing the power spectrum at two different scales. So the scales are, this impact is visible both at the small and at the large scales. So we already have to show you that we are going toward the detection of this 21 centimeter power spectrum. Here I'm also showing the current upper limits from a number of observatories. In particular, I want to highlight, so here I'm showing the 21 centimeter power spectrum fixing the redshift, so redshift 10, 9, 8, and 7 as a function of the scale of K. Here I want to focus on the purple points, which come from Hera, that observed that took measurement at redshift 10 and 8. So as you can see, all the three models that I've showed before, they are all consistent with these upper limits. However, at redshift 8, we see that Hera is getting closer and closer to rule out or confirm the models with a stronger power spectrum. And we expect to have more data from Hera in the coming year. And also, the big instrument here is SKA. SKA should do even better than Hera. So SKA should be able to observe some of this signal. And so to conclude this, we try to make some forecasts using, in particular, now I focused on the cyan and the red line, so different X-ray emission from POP3 stars. And I estimated here the observability. So here I'm showing a redshift 10, 9, and 8, again, the power spectrum of the two lines, the low X-ray and the high X-ray model. We use a package called 21 centimeter sense that allows us to estimate the 1 sigma error associated to an observation. In particular, this error mostly comes from thermal noise and cosmic variance. So the shaded region highlight the 1 sigma error region. So if we assume that we have 180 hours of observation data, you can see that the two models are basically undistinguishable because the two shaded regions superimposed to each other. But with 1,000 hours, which is not that crazy because it's basically 6 months of observation, and people are aiming to get 1,000 hours observation with SKA for the 21 centimeter power spectrum, we actually see that all these models, these two different models, are distinguishable at all redshift 10, 9, and 8. So this is really promising because it's telling us that we actually could be able to disentangle different POP3 star formation properties, in particular here POP3 X-ray properties, using the detection of 21 centimeter power spectrum. So yeah, I'm going to conclude the talk here. So as POP3 stars are very good at playing hide and seek, since we haven't detected them yet. But we implemented POP3 star formation in Meraxis, and we use Meraxis in particular to show that POP3 galaxies with a top-heavy IMF might explain the abundance of very bright galaxies at redshift larger than 12, and also POP3 star changed the 21-centimeter history, leaving an imprint on the power spectrum during the epoch of reionization, which hopefully it should be observable with FKA. Thank you.
Is your bubble sizes seem very large in your analytic formula? So if you extrapolate that to redshift 0, you're predicting bubble sizes of like 300 kiloparsecs or something, which is much bigger than the Milky Way.
Yes, but at the same time, well, it gets larger than the Milky Way because we can get actually out of the galaxy polluting with these metal bubbles. But these are not like a bubble coming from one specific star. It's coming from the combination of all the star formation episodes that will occur within the same galaxy. So you can imagine that initially we have all the different supernova explosions, and then they combine all together in one single larger bubble that is the one that propagates outside the galaxy.
I guess the question is it reasonable? If you apply that model to the Milky Way, do you get reasonable answers, or not really?
We couldn't look at the results at lower redshift because our simulation stops at redshift 5, mostly because it becomes very difficult to run because the computation is quite expensive to run the simulation down to redshift 0. So we actually couldn't track the evolution of the bubbles down to redshift 0. But this is something that I don't know if I guess that maybe like focusing on a smaller box that is something that we could do potentially to check the size at redshift 0.
Maybe rephrasing the question, if your bubbles were 10 times smaller, how would it change the results in higher redshift?
Or if the bubbles were 10 times smaller, basically no pollution from the external pollution would be completely negligible.
That was also your conclusion anyway, is that?
Yeah, they are mostly negligible, but not around redshift 5 and 6, which is it is interesting because, for example, recently there have been observed like a lot of damped Lyman alpha systems along those redshifts, and on those systems we can actually, well, we cannot measure the metallicity, we can measure the relative abundance of elements, so we can get some information on the metallicity of those systems. So that's why like the result at redshift 5, even if it's, is not completely negligible.
Yeah, interesting talk. For the global signal of the 21 centimeter, are there any like proposed instruments that might be able to see it, or is it kind of just hopeless?
So personally, I think, well, it's not hopeless because of course, like, so there are instruments that are, for example, we have REACH, which is a collaboration mostly from Cambridge University and the South African Observatory. So there are instruments that are improving the detection more and more, the sensitivity more and more, but those sensitivity would really pick up only very extreme or exotic models. For example, one thing that I haven't considered here, but it might be important, is the effect of dark matter, for example, like dark matter annihilation decay, or some weird dark matter interaction. Those can heavily change the signal, in particular boosting it, so making it much lower. So around the temperature of -300 or -400 millikelvin, and in that case, there is hope of rule out or detect those exotic scenarios. But if we are staying in the regime of, let's say, normal physics, our best chance is the power spectrum.
Okay, thanks.
Any other questions? That's the second one.
Just about the POP3 stars. So I mean, this business is interesting about the what kind of POP3 stars you produce. I guess I was just wondering if the field has converged on what kind of stars we expect. When you said top heavy IMF,
yeah.
But like how top heavy? Like, is there a sort of, as I understood it,
there is no convergence.
Kept going to lower masses. Is that?
So I guess that the main convergence is sort of like ruling out the very low mass stars. But again, there is also the impact of magnetic fields. So, for example, if you ask like people like Christoph Federer at the ANU, like they might disagree with that. But most of the studies kind of converge that the very low mass stars are kind of ruled out. So the one that like below 1 solar mass, and that's why like we are sort of like decided here to account only between 1 and 500 solar mass. But on the shape itself, there are really a lot of different possibilities. And that's why what we are aiming here to do is kind of like exploring different IMFs to see if different IMFs lead to some signatures. Because in that way you can say, oh, maybe the POP3 IMF, it's this one, or rule out the IMF.
So when you say top heavy, do you mean?
So top heavy is the yellow and blue. In particular, most of the result that I showed was like the blue one. So kind of like a log normal IMF centered at 60 solar mass. There are even more extreme cases, but we decided not to explore those scenarios because it seemed like too extreme.